Hello students, Mr. Muncie here, starting lesson 10-5 on tangents. So we've heard that word tangent before. SOHCAHTOA in a right triangle. The tangent of an acute angle is the opposite leg over the adjacent leg. This is a different use of that word, although they are actually connected. It's not really obvious why, but there is a reason we use the same word. So when we talk about tangent with circles and lines, a line is said to be tangent to a circle if it intersects the circle exactly once. So I could draw a line over here that completely misses the circle. I could draw a line like this that touches the circle twice. But I could also, in theory, draw a line that just barely touches the circle. That if I were to zoom in on my phone and zoom in and zoom in, that I would see that this actually just touches the circle at one point, and that line is said to be a tangent line, or tangent to the circle. That point is called the point of tangency. So that's what a tangent line is. Now I'm going to rotate the paper. Actually, before I do, let me add something. I'm going to add a radius to that tangent point. And I want to see if you can take a guess on what appears to be true. If I were to erase that circle and we just had this segment in this line, does anything appear to be true? And hopefully what you're noticing is it looks like maybe that segment is perpendicular to the line, forming a right angle. Now to figure it out, let me ask you this. Which line looks shorter? Which line has to be shorter, not look shorter? Which segment has to be shorter? The black one or the red one? Well, the black one is the length of the radius. The red one is the radius plus more. So that red one is longer. Black one is shorter. What if I draw this one from that center of the circle to the line over here? Black one versus red one. Which one must be longer? The red one has to be longer. Black one's a radius, red one's a radius plus more. Red one's longer, black one's shorter. If you think about it, any segment I draw from the center of the circle to the line is going to have a length of a radius plus more, except for one. This one is the only one that would just be a radius. So this is the shortest distance from that point to that line. And we know the shortest distance from a point to a line is always the one that makes a right angle. So it will always be the case that when you draw a radius to a point of tangency, it will always be perpendicular to that line. This idea also works the other way around, and it's a bit of a mouthful, but you'll see the theorem in your book. But the idea is that if a line intersects the end of a radius on the circle and forms a right angle, then that line is tangent. But really, if you just in your mind associate the idea of radius and a tangent line intersecting on the circle, always form a right angle, you'll be good. So let's look at this. Before the video, I just picked a point outside the circle and I drew the only two tangent segments I could draw. So I could have made a tangent line, but I just stopped as soon as I hit the point of tangency. I did the same thing over here. I could have made a tangent line, but I just lined up my ruler, and instead of making the whole line, I stopped at that point of tangency. Does anything appear to be true to you about these two segments? If I erase the circle, does anything appear to be true about those segments? To me, it looks like they appear to be congruent. So let's see if we can reason that out. The way we play around with circles is we draw convenient radii. There's a convenient radius, there's a convenient radius. They're convenient because they hit the point of tangency, and we just proved that that always makes a right angle. Same thing here. I also know this radius is congruent to that radius. And if I connect the outside point to the center of the circle, I get two triangles. Why are these two triangles congruent to each other? Well, this hypotenuse and that hypotenuse are the same segment, and they have a leg of the same length, so HL tells me they're congruent. And if these triangles are congruent, CPCTC, all the corresponding parts are congruent. So we were right, these two tangent segments are congruent. So here's the summary. If you take a point outside a circle and you draw two tangent segments, they will always be congruent. I will be referring to this as the ice cream cone theorem. I'll let you puzzle over why I would call it that. So, next. Here's a circle inscribed in a quadrilateral. So that means every side of the quadrilateral is tangent to the circle. And I want to know what x is. If the circle is inscribed in the polygon, you should see several ice cream cones. For example, from point T outside the circle, two tangent segments. I know these guys are congruent. From point S over here outside the circle, these are congruent. So if that's 3, this is 3. And if it says the whole bottom side is a length of 7, 7 minus 3 tells me this is 4. If from R to that tangent point is 4, the ice cream cone theorem says this is 4. If this whole length is 12 and that's a 4, this must be 8. And the ice cream cone theorem tells me if from Q to that tangent point is 8, from Q to here is 8, so x is 8. Ice cream cone theorem. Let's keep going. I made up a few problems. First one. You'll see some problems in the book asking, is this segment tangent to the circle? Is segment AB tangent to circle C? So it looks like it is, but they're asking us not to go by how it looks. If we were to zoom in on that, maybe what's really happening is that there's the circle and maybe that line actually touches it twice. So it wants us to figure out, is that really tangent? First of all, let's notice this 4. That 4 is only the distance from here to here. If I wanted that 4 to be the distance from here to here, I would have to draw something like this and say 4. But the way it's written, that notation means from here to here is 4. If this radius is 3, we know this radius is 3. So this whole length is actually 4 plus 3, 7. And the question is this tangent to that radius, to that circle? Well, if it's tangent, that's going to be a right angle. So let's figure out if that's a right angle. If that's a right angle, that's a right triangle. If that's a right triangle, 3 squared plus 6 squared would equal 7 squared. So I'm wondering, does it equal 7 squared? 9 plus 36, 45, does not equal 49. So this is not a right triangle. And if that's not a right triangle, that's not a right angle. And if that's not a right angle, then that segment cannot be tangent to the circle. So the answer is no. If we were to zoom in on that and these were the actual measurements, we would see something like that. For the remaining 3 problems, the segments are going to be tangent. So let's now look at this one. So suppose you were told that this segment is tangent to the circle and you have to find x. Well, if it's tangent, that means this is a right angle. If this is 10 and my radii are congruent, then I know this is 18. So how do I figure out x? What's the most important thing we've learned this year? Pythagorean theorem. We would do x squared plus 8 squared equals 18 squared. And if you go through that algebra, which I'm quickly going to do on my calculator, x comes out to be the square root of 260. If you want to practice your Pythagorean work, you can do that. When you simplify that, you would get 2 root 65. So there'll be Pythagorean work on these problems. Got a couple more things to show you, more examples. Let's look at the top one here. Same question. Solve for x. So again, if this is x and this is x, and this is tangent to the circle, that's part of the given information, then I would put a right angle here. And I could do a Pythagorean equation with the hypotenuse of 5 plus x. I'm going to let you guys work that out, and I'll continue this on the next video.